During this session I'm going to show how the equations of motion can be extracted from our prior graphical knowledge, so using distance time, velocity time graphs as a starting point. Now these things called equations of motion are going to be really important because they're a tool which allow us to consider and describe and make predictions about any situation where acceleration is constant. So let me take you through this step by step, and at the end we're going to then work with these equations of motion and we'll show you how useful they can be. So first of all, I'm saying we're looking at a situation where there is always constant acceleration. We can see that because my velocity time graph has a constant gradient and my displacement time graph has an upward curve. So we can say it's accelerating, but I know it's a constant acceleration due to the velocity time graph. So those are some useful bits of information. Motion's in a straight line because displacement is fitting the idea of the constant acceleration, and I know that displacement is 0 when time is 0. So these are the starting points for how I'm going to extract some equations which we can make use of. The terms I'm going to be using by the equations of motion are: S is for displacement, U is going to be initial velocity, V is going to be final velocity, A is going to be acceleration, and T is going to be time. So these are the algebraic terms which I'm going to try and consistently use throughout this. So first of all, how can I work out the average velocity? Now there's two ways to work out average velocity. I could just say the average velocity is going to be the displacement divided by time, or I could add up the initial and final velocity and then divide those by 2. Now as these two formulas both equal the same thing, it means that I can say that u plus v divided by 2 is equal to s divided by t, and this can be rearranged for s to show my first equation of motion, which is displacement is equal to the sum of the initial velocity and the final velocity divided by 2 multiplied by time. My next equation thinks about acceleration. How can we work out acceleration? Well, we work out acceleration as v minus u, final velocity, minus initial velocity, divided by the time taken, and that gives me acceleration. So if we rearrange this for v, what we do is find that v equals, or the final velocity equals the initial velocity plus the acceleration multiplied by the time taken. That's my next equation of motion. Now what I'm going to do is have the displacement equation. Here we think about how can we calculate displacement using the velocity time diagram. Well, what I'd do is I'd work out the area underneath the graph. So in this case what I'd have to do is first of all work out the area of the rectangular shape. So that's going to be the initial velocity multiplied by time. And then the triangular shape at the top here I can work out because that's v minus u, which gives me the change in velocity, multiplied by the time taken here, times by 0.5, because to find out the area of the triangle. Now I happen to know that velocity minus final velocity minus initial velocity times time is actually equal to acceleration times time squared. So I can input that, and this all can be shown as the total displacement is initial velocity times time plus half of the acceleration multiplied by time squared. The fourth equation I used by eliminating time. So I used the equations I've produced so far, and I'm going to eliminate time from that equation. So I can rearrange my acceleration equation. So t equals v minus u divided by a. I can substitute that, and then I can rearrange so that I can say, from another equation, I can say the displacement is u plus v times t divided by 2. Now if I substitute, what I can do is I'll work out that I rearrange that the final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. So this gives me the 4 equations of motion. Now these are really useful because I can see that looking at the equations, none of them have all of the terms in. So this gives me a wide range of options for trying to solve an equation or solve a problem if I only have a certain number of bits of information available to me. An example of this would be my example question. A police car P is stationary by the side of the road. A car S is exceeding the speed limit and passes the police car at a constant speed of 18 meters per second. The police car sets off to catch the car just as the car passes. If car P of the police car accelerates at 4.5 meters per second for 6 seconds and then continues at constant speed, so, the police car eventually takes a certain time to draw level with car S. So what I'm going to do is I'm going to work out some factors. State an expression in terms of t for the distance car S travels in seconds. Well, that's easy enough. I recognise that the velocity multiplied by the time will give me the displacement. I know that the velocity is 18. So 18 times t gives me the displacement. Calculate the distance travelled by the police car during the first 6 seconds. Well, this is a time when I know that the initial speed or velocity is 0, so this ut cancels out straight away, giving me 0.5 times 4.5 multiplied by the acceleration of the time squared, which was 6 squared, which gives me 81 meters. That's the displacement, the distance travelled in the first 6 seconds with a constant acceleration. Calculate the speed of car P after it's completed this. So now I look for another formula. V equals u plus at. I know that u equals 0 because it's initially at rest. 4.5 times 6 gives me a final speed of 27 meters per second. Then state an expression in terms of t for the distance travelled by the car during the time it's travelling at a constant speed. Well, I know that's going to be 27 seconds times the time that it was travelling for. Now, what I'm going to do here is I'm going to combine these information. I want to find out the point when the cars draw level with each other. So that means they must have travelled the same distance. So the distance of the speeding car is always going to be 18 times t, whilst the distance travelled by the police car is going to be 81 meters for the initial acceleration, and then 27 multiplied by the total time. But remember, the total time is going to be t minus 6 because there was 6 seconds of acceleration. And if I solve for t, it's going to give me an answer of 9 seconds. So here's just one example of how the equations of motion can be really useful in solving problems involving constant acceleration.